Hey everyone, thanks so much for joining us today. It is Thursday the 24th. My name is Sue Ewig and I'm with the Global Partner Marketing Group for AI and Machine Learning for AWS. And we're really excited that we're back in the groove of doing these webinars every couple of weeks. Today's webinar is going to cover random cut forest. And we've got Chris Burns joining us today. And you guys have heard Chris Burns a couple of times. He's one of the PSAs on the AI/ML partner team. He's based in Austin, Texas, and he's ready and raring to go. If you have questions during today's webinar, there is a question little section on the right nav of your GoToWebinar screen, and feel free to pop your questions in there. Chris is going to try to take as many as possible, but if he doesn't get to your question, we will summarize those questions in a follow-up email, answer them, and make sure that we share them with everybody. So that's a funny one. Thanks for asking. Just asked a question, what is algorithms? Which is, yes, we're not going to be answering that question today. If that is a question you have, you are on the wrong webinar. But thanks for the humor. It's good Thursday morning humor. So Chris, without further ado, why don't you take it away?
Thanks for the intro, Sue. Let me share my screen. It's not sharing.
Hey, here's a tip. I should make you the presenter and then you can share your
Oh,
screen.
you know,
So now it should work. My apologies.
it's still grayed out. So let's see
That's
here.
weird. Hang on. There we go. All right. Sorry, guys.
All right. Looks like I am sharing now. But now the question is, what can you see? Can you see the Jupyter
Um,
Notebook, or can you see
right
the
now we see the
slide?
Jupyter Notebook, and here comes the PowerPoint. Oh,
Okay.
that's
Okay.
a fantastic picture.
All right. So can you see my notes and everything, or can you just see the PowerPoint?
I can see the PowerPoint slide and the next slide
Okay. Let me change the view
and the
here.
notes. Yeah. So
How about now?
there we go. Full screen, just the PowerPoint. Thanks,
Okay.
Chris.
Okay.
Thanks
Sorry.
everybody for hanging on. Hey,
Too
that
many
actually worked
monitors.
out okay. Now we had a time for more people to join. So welcome everybody.
Okay, so let's go ahead and get started. Thanks again, Sue, for the intro. And today's deep dive is on the random cut forest. This is a fundamental algorithm for the whoever asked what the algorithm was. I'm going to see if you can get it with your context clues. This is a fundamental algorithm to data scientists, to machine learning practitioners. It's one that it still excites me, to be honest with you, because of its fundamental nature. And we get caught up in the neural networks, we get caught up in the new hotness and what's coming out on archive.org, and sometimes we forget that sometimes these shallow learning, we'll call them, algorithms are here and they serve a legitimate purpose and they have a lot of versatility. So my profile picture there, I had to update it and I didn't have time to get a proper headshot, so I figured, hey, what the heck, have some fun with it. So the next hour, I'm going to go quickly because an hour is not a lot of time to spend with you and share as much information as I want to, but we're going to break down the RCF. We're going to talk about how it differs from decision trees. We're going to talk about the idea that it's a black box, when to use it. I'm going to jump into Jupyter Notebook and do a quick bit of live coding just to show you how to get one ready to train and deploy to a SageMaker endpoint. And then we're going to spend a little bit of time on anomaly scores, because that's really what the forest is all about, is anomaly scores, how to get those to go to work for you. And then whatever time we have left over, we'll have Q&A. So make sure you get those questions ready. And once again, I wanted to apologize if you originally scheduled this webinar. This was meant to be done immediately after the new year. And in full disclosure, I shut it down over the holidays for a few weeks just to give my brain a rest. And when I came back to work, I was not ready to present. So nobody wanted that. You didn't want that. I didn't want that. So we pushed it off. So apologies for that, and thank you for your patience. All right, so I talked about the fundamental nature of random cut forests, and from the looks of my attendee list here, looks like we have a lot of folks that are not did not grow up here in the States. Maybe you did, maybe you didn't. But this is a picture from Sesame Street. And I love this algorithm because it's about finding anomalies. That's the primary use of this algorithm. And this goes back to something I learned, most of us learned at 4 or 5 or 6-year-old. There's a song attached to this. I was going to play the song and see if I get stuck in your heads, but I figure that's not very polite. And it was, which one of these is not like the other? So we talk about anomalies, we talk about which one of these is not like the other. There's so many business use cases to find that anomaly. And so this is the algorithm that's very simple to put together. The data sets are very, very simple, and it's very, very powerful. So you're going to hear that theme over and over again for the next hour. I really want you to go out and I want you to play with these. If you don't have any of these in production, you really should find a way to get them into production, because what we're going to see in the coming months and in the coming year or two is you're going to see these ensembles where you bounce an inference off of one model to another model to another model. And I guarantee you that anomalies are going to play a factor in that. I guarantee it. So let's move. So another point I wanted to make here, when I'm laying out a solution that's going to involve inference and models, I like to anthropomorphize. So that's a really big, crazy word, anthropomorphize. It really just means to give something a human characteristic. So when I design a solution with inference, I kind of treat it as an agent, an AI agent, and I say, okay, how do I want this to act? How do I want it to perceive its environment? What do I want it to do when it sees something? And so anthropomorphize is a term I like to use. This is a great one for random cut forest. Don't imagine this as a model. Imagine it as an AI agent, and what do you want it to do? What do you want it to see? And we're going to get into the details here. A couple of great data sets, or when we talk about anomalies, anomalies can mean many different things. Time series spikes. So if you have time series data and you want to find these outliers, this is a fantastic model for doing that. And also periodicity or periodicity. I've heard it pronounced several different ways. You can just read it and pronounce it in your head however you'd like. And a great example of this is, if you've ever done any game development or done anything over the network, you have latency. That's the measured delay in packets. But then you also have jitter. So if you look at this chart here on the right, and the latency increases and decreases, then that's called jitter. It's a measurement of chatter on your network. So this periodicity is a way to tell if something has changed its temporal state, or it's taking more time or less time. Both of these are great examples to put to use in the random cut forest. At the end of this point, we're going to share this, by the way. There's a link to a website that has a lot of great outlier detection data sets, and you'll find examples of both of those at that link. Okay, so the random cut forest versus the decision trees. If you're using your context clues here, you have forest and you have trees. So we can assume safely that the forest is made up of many trees, which is absolutely what that is. Now, a decision tree, what you have here on the screen is a diagram of a decision tree. It processes the entire data set that you pass to it. Now, this black, red, and yellow icon is my poor man's version of a data set. So just imagine that being some features, many, many observations all up into a data set. And what we see here is when we begin, it's going to be split. It's going to be split based on the decision that the decision tree makes. And so we have 50% here, 50% here. Obviously, 50% is not the absolute value. It could be multiples there. And it keeps breaking that data set down until we get down to the leaf nodes. But the whole point of this is that the decision tree uses the entire data set. And what we're going to see differently in the random cut forests is that it does not use the entire data set per tree. It grows a forest, okay? And now you've heard of growing multiple decision trees from a single data set. That's called bagging. MATLAB refers to it as an ensemble. If you work with MATLAB or not, it's a mashup of the words bootstrapping and aggregating. So it's not boosting. Boosting is when one entity learns from another. These trees in a random forest, they run in parallel, and then the forest calculates the mean of the leaf nodes. And so again, I apologize for my poor man's graphics, but what this is meant to represent is that this tree is going to get just some kind of random chunk. It's not going to get to pick the features. It's not going to get to pick the observations. It gets this random sampling from the data set. And now this is where we get to the point where people are calling them black boxes. We'll get into that in just a moment here. But the logic is that a large enough number of uncorrelated errors will average out to zero. So the more trees, the more accuracy you should have. Now, why do we want the average to be 0? It all goes back to the mean squared average, MSE. Everything regresses to the mean. That's a phrase I love to use. If you've never read the book Thinking Fast and Slow by Daniel Kahneman, Kahneman, as soon as you get done with this webinar, you need to go get that book because it is a fantastic book. Granted, he is a psychologist, but the rules of statistics and scientific theory apply very, very well to us in the AI and machine learning space. Anyways, sorry about that shameless plug, but it's a great book. And we want to, so regression to the mean, we want to find that global minima. And remember that MSE, mean squared error, can be expressed as the sum of the squared bias of predictions, the variances of those predictions, and then the randomness in the data. We can't control the randomness in the data, so that leaves us trying to minimize both bias and variance. Hence the multiple trees. If decision trees are usually variant high, so they're very, very dependent on the data set that you pass to them, and they have a relatively low bias. The random cut forest was designed to balance that bias as well as variance. Now, the idea that they're black boxes. So this is something that I like to debate about a little bit. You can choose the number of trees. And as I mentioned, the number of trees, as they increase, you will increase your accuracy until you reach a constant point. The nice thing about that is you're not going to overfit. You can't overfit a random cut forest. It'll only reach a constant and then stop because your averages are only going to average out to a lowest global minima, and then it's done. You can choose the number of random samples per tree. So there are some opportunities here for hyperparameter optimization in SageMaker. If you have a couple of parameters you want to play with, feel free to throw that into the HPO mix. What you cannot control is which features go to which tree. Our example really only has 2 features. So technically speaking, it's 1 feature, but 2 features, so we don't have to worry about that right now, but these can become increasingly complex for classification purposes rather than just temporal measurements. And you cannot control which observations go to which tree. So you can't control which of your instances, which of your rows in your data set, to use a layman's term there. This is where people talk about random cut forests as being black boxes, because you can pass the same data set to a random cut forest on multiple occasions and you're going to get different anomaly scores. So people get all up in a tizzy about the repeatability of this. Now, what I'd like to stress to everybody is that the randomness is contained within a deterministic data set. And what I mean by that is once you have your data set, yes, you can randomly come to different anomaly score conclusions from that data set, but the randomness cannot break out of that deterministic data set. It does not introduce any kind of feature engineering or does not create features from multiple independent features. So stress that to your to your clients, to your customers when they talk about, oh, it's a black box. And also, we'll get to a slide here in a few minutes when we talk about when is the best scenario to use these. So if you've got a healthcare life sciences client who has got a lab environment and needs absolute chain of custody and repeatability, this is not going to work for you. But if you have something like the example we're going to use is the New York taxi cab data set, where you have a lot of room to play around a little bit, I guess that's the phrase I'll use, then random cut forests are fantastic. Okay, so when to choose? As I steal my own thunder from this next slide here. So when the application requires a greater accuracy and repeatability is not paramount. Now I chose the word paramount here on purpose. I didn't want to use the word important. Repeatability is always important and it should be stressed, but paramount means that it's the deciding factor. It is the critical factor and it's the most important factor in that particular solution. And then also when you need lower variance is more desired than a lower bias. I wish I could give an attribute or a credit to this picture. I found this picture in an article, and the individual apologized, just like I'm apologizing to you, because he found it in an article. And so the source is unknown. I should, I guess, just put source unknown there. But if you know who created this, send me a note, let me know so I can give him credit in a proper citing. I've been talking about variance and bias quite a bit here for the last few minutes. I wanted to just throw out a quick refresher on this. Now this is summaries. So if you have a particular definition of bias in your head and this doesn't comply with that, just understand that I'm trying to make this lowest common denominator. We have a lot of wide-ranging folks on these webinars, and I try to go to the least common denominator. So if you're a professional, you can send me an email and say, hey, that's not right. You should update that. But so a bias is an assumption made that attempts to make your function, your utility function or your X function easier to learn. So parametric algorithms, they're going to tend toward a higher bias, like linear regression. But decision trees, nearest neighbors, SVMs, the shallow learning family, if you will, they have less bias. And that's because they are higher in variance because they're dependent on their data set. And variance is, of course, the amount of change in your function that you get from the different data sets. This is where your linear regression is going to be a little bit more tolerant, and your algorithms like decision trees are going to be higher variance. So enter the forest, the random cut forest, where you have multiple decision trees. You can take the mean of those scores, average them out, and you get this great balance between a bias and a variance without worrying about overfitting. Oh, I'm flying through this super quick. So 20 minutes in, what I'm gonna do now is I'm gonna change to a notebook, a Jupyter notebook here, and I'm gonna do some semi-live coding. It's not quite live coding. Oops, I apologize. Let me stop that. Sue, can we see the Jupyter notebook? Can I just get a check on that? Okay, Sue must be on mute. So let me check my comments here. All right, so I'm going to assume we can see this notebook. Although I don't have verification of that. All right, so I'm gonna cut and paste a little bit. There's no sense in watching me type some of this stuff. Now I'm using the new Jupyter Labs available in SageMaker. So I'm still in SageMaker. I didn't log in and load up this particular project, but just know I am in SageMaker here. I'm gonna import my usual suspects. Hopefully these are familiar to you. The Bato 3, the Python core. Bato core, the Python libraries. Here's our SageMaker SDK. We're going to use pandas, matplotlib, and I'm also bringing the SageMaker SDK in because we're going to use the random cut forest. I'll go quickly line by line. So I'll try to mix this up so it's a little bit something for everybody. I'm going to establish an S3. Actually, I don't need to do it anymore. I'm going to download this directly from GitHub. I'm going to establish a bucket. Everything is in Chris Misk. And then a prefix. So what this prefix is just going to separate this project from all the other projects that I dump into Chris Misk. And then execution role. Remember, SageMaker is going to provision resources for training as well as deployment. So we have to give it a role to use when it's provisioning those resources. We're going to go grab this data set. And I do apologize. I'm using a pretty boring manicured data set. It's called the New York Taxi Cab data set. It's out here. This Numenta is one of the, they have a lot of these data sets in that outlier detection data set source that I told you about. So what I've done here is I've just used the URL lib library to go get this data and copy it down in the name of F here, which is the nyctaxi.csv. And then I've read it here into a pandas. So nothing outlandish thus far. And if we want to take a look at this data, very simple. These timestamps. Now, one recommendation here I have, I'm not going to do it in this notebook, but if you're working with timestamps, I'm kind of old school. I like to go to the second since the epoch. There's a conversion that you can do on that whole column in a pandas. It's going to change that to a 64 bit integer. It's much easier to work with when you're in code, and it's very simple to convert that back to a timestamp when you're done. So just a bit of advice there for you. And then the value, and this has something to do with the number of taxi cab rides per day or something like that, or per time segment. We're gonna take a quick look at this data. So I'm going to use the magic command, matplotlib inline. Remember, I imported my matplotlib, up here with my other imports. And I'm going to set the DPI to 100 because there are a lot of data points in here. And then we're going to plot this. Now, what you see, obviously, this is a data set meant as a perfect match for this quick webinar because we see these anomalies very easily. in the data set. The real world, unfortunately, will not be so clean, but that's what we're here for, right? Now, I use the word magic command here. I got a couple questions in my last webinars about magic commands. When you see this percentage sign, excuse me, we're using a magic command. So if you want to know what the magic commands are, just type in magic without the caps lock. All right, and you're going to get oh wow, Jupyter Labs doesn't break it out into a pop-up window, but you're going to get a full explanation of all the magic commands, what they do, when to use 1 percentage sign, when to use 2 percentage signs. So just a little bit of another FYI for you there. So what we're going to do now is we're going to actually instantiate the class that we're going to use to fit this. We're not going to fit, I'm not going to sit here and make you watch this model be fit and deploy it. I'm going to jump back into the PowerPoint here in a minute. Again, this notebook will be available to you at the end of this webinar. There's a link to the full example notebook in SageMaker that's much more verbose and explanatory. So what we're doing here is we're creating the actual random cut forest class. So again, our role training instance is 1. So this is, I'm going to pause here for a moment because this treats its data set a little bit differently than some of the other SageMaker built-ins. The training instance determines the number of what's the word I'm looking for? It's going to break your data into X number of parts, and X is equal to the number of instances. So had I changed this to 4, then this call to record set that we're going to go over in just a minute would have broken my data set into 4 instances and passed 1 to each training instance. M4 and C5s are the recommended instance sizes for training RCFs. RCFs don't benefit from GPUs. So good news and bad news there, however you want to take it. It's much cheaper. And, you know, CPUs maybe not quite as performant in some training, but random cut forest train just fine without GPUs. Our data location, this is where our data is going to be for training, and then where our model is going to be put. So if you've seen these webinars before, if you've used SageMaker at all, this should be quite familiar to you. Here are the only 2 hyperparameters, well, there's actually 3, that we can manage on the random cut forest: the number of samples per tree and the number of trees. Now, the number of samples per tree can go from 1 to 2,048. I don't recommend 1. The default's 256. I got 512 here for some reason. I just felt like putting in 512. And then the number of trees is 50. The number of trees can go from 50 to 1,000. So if we had more time, if you're experimenting with this, you may experiment with going from 50 to 500 to 1,000. Give yourself a distribution there of see what your anomaly score looks like. Now, I did this on purpose here. I've commented this out because there's a lot going on in this one line of code. We see that we have our class, I'll call it class, RCF.fit. And what are we fitting? We're fitting the RCF.record set, which is a call to a built-in function of RCF that we're going to go over just a little bit. And what are we passing to the record set? We're passing the taxi data .value as matrix .reshape. So a whole bunch of stuff going on in this line. If you're new to Python, if you're coming to Python from a different language, there's a lot going on in that one line of code. So I'm going to break this out. I think it's worth the time, worth the 5 minutes. Now what I'm going to do here is I'm going to instead of having this all in one line, I'm going to break it out into a few lines so we can see here. So I'm going to create this temporary data set called new data, where I'm just taking this pandas and I'm running the as matrix command so that you can see what it does. We see that we now have new data is now an ND array. It is not a pandas data frame, and we see our shape there, 10,320 entries. So just that single vector. Now that's where the reshape command comes in. So we're going to reshape this. And now we see the shape now is this -1 here is telling the reshaper of the NumPy array to just use the default number of instances of rows. And so that's why we've preserved the 10,320 instances, but now we have some dimension to it. So that's the reshaper. And now we need to pass this to the record set. And again, record set is a function, built-in function of the random cut forest that does quite a few things. So I've printed here the object that was returned from the record set, and here's what we get. So we get an object of .record set, which is now usable for fitting on the RCF, but we also get this manifest file. Now, if I were to go and open this manifest file, you would see, because I'm using one instance here, as a matter of fact, I think I set this up. Yeah, so this is an instance where I had 4 training instances, so I got 4 PBR files. It split the data set evenly over 4 objects to pass to each instance. This one, if we were to visit this subfolder, we would see 1 PBR. Now, at this point, we would be ready to train and ready to deploy. I'm not gonna kick this training off because there's really no value for you doing this now. There's more value to do this on your own. And then after the fit is complete, then we can just deploy this endpoint. I don't know if we need an M4 for the endpoint, but and then we'd be ready to do some anomaly scores. Now I'm going to jump back into the PowerPoint. Check my time. We're doing good. Okay, so the RCF is going to compute anomaly scores for us. So this here, observations, this diagram, that's what we passed in. Those are the values. If you remember, there's the exact same ones. That's the head from the pandas command. And what we get back is we get back these scores. So let's talk about these scores for a minute because this is important. A high value indicates that the data point is abnormal. A lower value means that it's not. Now, abnormal does not equal anomaly. What is an anomaly is really going to be up to the business process that you're building for. Because let me take an example. The definition of an anomaly is something that deviates from what is standard, normal, or expected. So if it's just because you don't expect it, doesn't mean it wasn't expected. I'll give you an example here. If my VPN security mechanism suddenly sees a logon from an unknown IP address for me, it's not normal. However, if in the perfect world, if it were smart enough to know that I was on a beach in Bali somewhere, or Bali trying to do my work, it would say, okay, this is not normal, but it's expected because Chris is in that code that has this IP range. So what is an anomaly is going to be up to you. Now, the threshold to consider what anomaly is, the industry standard, if you will, is 3 times the standard deviation. Now, that's in either direction, remember. This particular example was just a count of cabs. We couldn't have negative cabs. But you may be using this in an instance where you drop out. That's called a temporal shift or something like that. So I do apologize. I forget the exact word for that. But there's a word for when there's an absence of activity. So still an anomaly, but going in what we call the negative direction. And then that's also known as the 3 sigma limit heuristic. So 3 times is pretty common. 3 times standard deviation, and it's common because of my all-time favorite chart right here, the bell curve. 3 times standard deviation, you see, puts us here, 3 times standard deviation at the 99.9 percentile. Now, this may or may not work for your business solution. So you need to play with this here, and you need to understand. You got to plug in some domain knowledge. What are you working on? Because 3 times standard deviation puts you at 99.9%. Now that's very, very, very odd. So there could be some shenanigans happening between 84% and 99% if this is a security application or something that you might want to check out before just waiting till the 99.9% profile. So I suggest a more nuanced approach to this. And so what I suggest is anything 1 standard deviation in either direction, there's nothing to see here. Okay, then when you get into two standard deviations, that's what I call EER. That's explore, explain, retrain. Explore, explain, retrain. So that means there's something going on out there. Maybe it's normal, just unexpected, and so it wouldn't be considered an anomaly, but we need to get that into our data set and retrain so that it pushes it back towards the center of that bell curve. And then out here you have the MEER, and which is mitigate. Mitigate, explore, explain, and retrain. And mitigate means if this is an application for I'll use the example of a login, and your random cut forest is detecting some anomalous behavior way out of there, you would not allow that to happen. You'd mitigate that. You would say, okay, this is not going to take place. We need to investigate, see what's going on here, because the chances of you a great example is the credit card on Black Friday. You hear about people go out to the stores and they spend one store, then they spend another store and another store in rapid succession, and they would get their card declined. And because one of the problems was credit card companies one of the most common uses of fraudulent credit card activity is somebody would use their card at the store and then they drop the card or lose it or something like that, and then somebody pick it up and use it immediately, either at that same store or a nearby store. So that's a great example of mitigate, explore, explain, and retrain. All right. So, oh, hey, look at that. That was it. That was the Q&A. So where are we at? We are at 35 minutes. So we may wrap up a little bit quick today. I'm going to go ahead and go to the questions. And hopefully we get more than just what is algorithms.
Chris, do you see the questions that are in here?
I'm popping them out right now. So actually, everybody
Okay,
can see the
great.
questions.
Just want to make sure. There's a couple in here.
Okay. So here's a great one. Is random cut forest the same thing as random forest? Sue's, you hear Sue laughing. We were just talking about that. I was trying to get to the bottom of why we added the word cut to this to our, and the answer is yes. They are the exact same thing. And the only conclusion I could come up with that sounded semi-educated was that I realized that random forest is trademarked. So a company like Amazon, unfortunately, we would not be able to call anything random forest if that trademark is legitimate. So what I was able to discover was random forest is trademark. So we added a random cut forest, and obviously the cut is probably representative of how the anomaly score is calculated and how we take that mean from the leaf nodes. So it is the same thing. And we had a question here at 20 minutes ago asking if we lost audio. So I'm hoping that it was just the individual.
We did lose audio for just a couple seconds. It kind of cut in and out. So,
okay.
But I think
yeah.
it was.
So here's a question: Can we see the notebook? Yes, I'm gonna pass that notebook out with this webinar, as well as the one that's built into SageMaker. The example is there. So, like I said, it's much more verbose, a lot more terminology to walk you through what's happening.
There's another question here, Chris. What actually causes the algorithm to claim something has a high anomaly score? What's the basis for that metric?
Yeah, and the basis for that metric is so the anomaly score is a mathematical calculation based on the mean of the decision tree. So the decision tree is going to say, what it does is it finds the mean. And so we have that baseline and it gives it a numeric value of 0. And then when a instance comes in, an observation comes in, and it's passed through that random cut forests, we'll call it it's the JSON file. That's basically a calculation of the forests equations, and the score is high, we know it's far away from the mean. So based on the features that were in that instance, it does not match anything that is considered mean or average or what's normal. So that's where we get the abnormal high score. But remember the cautionary tale on calling something an anomaly, because an anomaly is something that is unexpected as well as abnormal. So how to tune the hyperparameters, like the number of trees. So that's when I'll go back to this notebook real quick. And when you instantiate this class here, now I'm using a Jupyter notebook for this. Now let's be honest here. This is not something that I don't know if I would use a notebook in this with production. This is just I've got 25 lines of code. This is something that we can run in maybe even a Lambda function and kick it off to SageMaker. I don't need to be in a console doing this, but the number of samples per tree right here, and the number of trees also right there.
Chris, here's a question. Is random forest used with weak ensemble learners like GBM for ensembling?
Let me see. No, it's not. The random cut forest, let me go back to my slide. Back to the slide. So GBM, unless you have a decision tree that utilizes GBM for some reason, the random cut forest is more of an orchestrator. Think of it as an orchestrator, and it's just going to grow many, many trees and it's responsible for just chopping up, randomizing the data to pass to the individual trees. And so you're going to get back these values from the decision trees, and then it simply takes a mean from those scores. And we have a question here: how is it unsupervised? It's unsupervised because I didn't label any of this data. Let's go back to that snapshot of the pandas head here. Here. Now recall when you issue the head command in pandas, it adds these boldened indexes, and it also adds these column values here. I'm sorry, these column names. So what we have is we have a timestamp and a value. So I haven't labeled anything here. I haven't said what is anomalous, what is not anomalous. This is unsupervised because I simply pass in that data set. It's going to calculate based on these values and timestamps what the mean is. I keep using that phrase mean, but that's really what this is, in essence, is what it's about. And then it's going to determine, when you pass in a fresh observation, calculate by the same algorithm, the same score, and it's going to say this score is high, it's abnormal, appears to be abnormal. Okay, so here we have another question on periodic data. The idea of a mean and being far from it doesn't quite make sense. So let me go back to my slide on the jitter. Okay, so if we were to pass in a data set for and measuring periodicity, this latency is going to also be a time series, and it's going to be very, very evenly spaced. Say that this is 4 microseconds apart. What happens here is that 4 microseconds, and all of a sudden you see 16 microseconds. It would be the equivalent of, going back to, I do apologize, I'm going through here very fast. This value attached to a timestamp would be very, very consistent before 4 microseconds, and then 16 microseconds. It's just an abstract. You can engineer that in different manners to pull out the differences. You may need to do some normalization depending on what you're doing. So periodicity, I guess I'm just going to say it twice, both ways every time, you can detect what's abnormal based on the duration of that event. Let's see, can we choose the number of SD that needs to be considered? SD, I'm not sure what SD is abbreviating. So I'm going to think about that for a second. Do we have to tune the number of trees in a random forest? Yes, absolutely. This particular example, I started out with 50, which is the minimum. And what we did, I guess I would have had some added value if I would have actually done some charting of the anomalies so we can show what was anomalous and what wasn't anomalous. Because visually speaking, if I were to base it off this image that's on the screen right now, these ones highlighted in yellow, I want those to show as anomalous. So I want the score to be sufficient enough that these pop out to me as anomalous. So if you run 50 trees and you find that you're not getting enough variation in your anomaly scores, then go ahead and add 100 trees, because what you're doing is you're going to try to increase your accuracy. And there's no danger of overfitting, so you could actually just increase it to 1,000, and really it's just a matter of kind of brute force on that RCF algorithm for training purposes, because the more trees you add, the more resources and the longer it's going to take. So the graph with anomaly was shown in a notebook. How we decided that particular value can be considered as anomalous. Let me go back to the notebook. Okay, so this is just a simple plot in matplotlib. And I could probably show this in a little bit cleaner way, or narrow the scope down. But this value, it's just plotting the value of these timestamp and value. So what we get here is we get 0 to 10,000 observations, and then this is the score here. So we see that most of these scores are very, actually the mean would be somewhere in here. This one, because of its score, this is a simple scatter plot, and we see that pop out just from observation that this is very, very, very anomalous. Okay, so I got some clarification. Standard deviation, so I apologize for that. So can we choose the number of standard deviation that needs to be considered to, or yeah, absolutely, because standard deviation is an abstract, it's a human perception. when I get my anomaly score back, remember, it's just a score. It's just a mathematical calculation that's trying to tell me how far away from the norm or from the mean that observation is. So one standard deviation or two standard deviations or three standard, that's entirely up to you and the application that you're trying to apply to whatever business problem you're trying to solve to. So hopefully that answers that question. Let's see. Trying to actually quite a few questions here. So can a random forest be used as a stacked ensemble with GBM? Well, yes. I mean, when you talk about ensembles, there's really the sky's the limit there, and it's really about data. It becomes a issue of data inputs and data outputs. When we say let's back up. Ensemble simply means more than one. So if we have an ensemble of models, maybe we want to pass an inference to one model to predict some value, some feature, something. And then that prediction, it becomes the input for our next model. I've just created an ensemble. So if I wanted to use a gradient boosted machine, remember we're moving from boosting. The trees is about bagging. It's about bootstrapping and aggregating, where GBM's gradient boosted machine is about boosting. And boosting is dependent on one entity taking the value of another entity before it can make its calculations. So if you wanted to do an anomaly detection with a random cut forest and a GBM on the same value, and maybe average those out to achieve your score of what's anomalous and what's not, that could provide some fantastic insights that you wouldn't get with just one or the other. But can I take this anomaly score and then pass it to a GBM? Probably not, unless I wrap some additional features around it. I'd need to hear the business case and the actual solution we're trying to solve to understand that more. Okay, so somebody's asking how we calculated the score once more. So we're going to go back to the diagram of the tree. Okay, so this score is calculated exactly the same as a decision tree would be calculated. If you need a refresher on decision trees, I actually recommend the scikit-learn example on decision trees. It's fantastic. You can write it out in a few lines of code and you get the, it's going to go over the entropy. It's going to go over all the aspects you would need to understand how a decision tree reaches the calculation that it does. Now, what a forest does is it simply takes all those leaf nodes from our decision trees. In this case, there was 50, and it takes the mean, it takes the average, because we randomized our samples, we want those averages to come out to 0. We want to get that lowest possible number, and so we take the averages of these rather than just taking an entire data set and passing it into a single tree, or multiple trees with the entire data set. Let me see here if I got them all. All right, I think that was it. So let me see here from Q&A. Yeah, so here's some links that this will obviously be included with the distribution of this webinar. So with that, we wrapped up a little bit early today. Random cut forest, I kind of sped through it a little bit quickly. I do apologize for that, but hopefully you got the gist of it. They're very, very powerful, very, very simple to use. You should be using them. Even if you don't have an absolute specific use case for them right now, you should be getting familiar with these, because they will become, like I say, a cornerstone of most ensemble in the near future. And anomaly detection is going to be the norm. It's going to be the norm for many, many different applications. But that's it for today. If you want to drop off now, thank you very much for attending. And just to keep the last bit of housekeeping, one more reminder: if any more questions come in the next couple of minutes, I will take those down and answer them, and we'll pass those answers out along with this webinar. So there'll be a recording of me stuttering and stammering for the last 45 minutes, and then also the slide deck I used, as well as the notebook.
Awesome. Thanks, Chris. Thanks, everybody, for hanging on. Lots of great questions. Next webinar happens in 2 weeks, and Chris Burns is going to be at it again. So hopefully we will see you guys in 2 weeks. And any questions between now and then, I just popped Chris's email into the chat. It's burnsca@amazon.com. So any additional questions, you can shoot him a quick note. And hope everybody has a great day. We're going to log off now.